Hello, Science Alliance! Alright, IGCSEers. This is the last lesson of the energy module. And then so after this lesson, we're exactly halfway through the whole of IGCSE physics. Isn't that amazing? And then we're starting solids, liquids and gases next week. Right, because we're going to do about radiation today. So we've looked at how heat travels via something called conduction and something called convection, which we will recap. And we're doing radiation today. I could make this lesson really simple, but because, like, you know, there's not a bell going to ring in half an hour and I have to pack you all off and sign half your reports and stuff and pack away equipment, I'm going to do a little bit more than I would normally do in a classroom to try and explain what radiation actually is, because you often don't get that bit. We're going to make something called a Leslie cube. We're going to make our version of a Leslie cube, which looks like this. I know, you're saying it's not a cube. You're right, that is really the least of this Leslie cube's problems. So we're going to anyway, because the whole point of this lesson is that you remember stuff for your exam and it helps your understanding, and I'm sure that will. So get a piece of A4 paper. You need to do what we always do with A4 paper in theatre of science. You need to fold it in half so the short edges meet, and you need to do that 3 times in total. So fold it in half once, and then fold it in half again, and then fold it in half again. Hello, new people who have just joined us watching live. I don't want to put myself down, we haven't missed anything. This lesson is on radiation, and so far we have folded a piece of A4 paper in half 3 times. And then open it out, and you should have 8 little rectangles made from creases, okay? What you need to do, once you've got your 8 rectangular creased bits, is you need to get a pair of scissors and cut off 1.5 rectangles. Is that all right? Get 8 rectangles on a piece of paper and then cut off 1.5 of them, and then you can just get rid of that bit. We don't need that bit anymore. Is that all right? Whenever this is not physics teaching, this is crafting. I get very nervous when I'm crafting. You're all right if you're watching on catch up, because you can skim ahead or pause it, but people who are watching live always get really panicky that they're shouting, "You're going too fast!" or "Oh, it's so boring, get on with it." Anyway, piece of paper, cut off a rectangle in half, discard that bit, then can you fold this whole thing in half the opposite way, so now the long ends meet. I will actually start telling you about heat transfer in a sec. Do you know what? Let's leave it there. Let's just leave it there, and I'll just do a little recap of what we did last week. While some of you are catching up, right? Fold a piece of paper 3 times, cut off a square in half, and then fold the whole thing in half so the long edges meet. Okay, right. What did we do last week? We looked at how the particles are arranged in solids and liquids and gases, and we looked at how solids, all the particles are very close together. They do vibrate, everything's vibrating a bit, but they sort of vibrate on the spot. Gases, the particles are not bonded together, they're free, very far apart. And liquids, it's kind of like a ball pool. Actually, the particles are all touching, but they're not quite as close together as solids. They are always moving around each other. And we looked at something called conduction and said that this is how heat energy travels. And it's generally how heat travels through solids. And metals, we learned, are particularly excellent at conducting, allowing heat energy to pass through them, because they've got these things called free electrons. So the protons, these big red particles here, are like just vibrating on the spot. But the blue particles, the electrons, they're free to just whiz around. So if there was something very hot down here, the protons would sort of start vibrating more and vibrate into each other more, and that would pass the heat along like dominoes. But also the free electrons would just kind of get very hot and then whiz the energy to the other side. So yeah, that's conduction, and it happened. Oh look, I wrote it all down for you. That's conduction, and metals are very, very good conductors because their particles are close together and they contain free electrons which carry the energy from one side of the metal to the other. I just said that, but doesn't it look nice written down? And then we asked, are liquids or gases good conductors? And we answered, no, they are not, because particles aren't close enough together, right? It takes a long time for the heat to travel through them. We looked at convection as well. This should not be new use. New use, how heat travels through, I don't know, like a pan of soup. The bottom of the soup gets hot, so it rises up, but then it's at the top, so it cools down, so it sinks, but then it gets hot again, so it rises up, and that's what we call a convection current. Whew! So that's what we did last week. And then I showed you this homework sheet, and said, have a go at that, and we'll mark it now. How are you doing with your bit of paper? When you folded it in half, long ways, you need to cut it, but don't quite cut along the halfway line. It's really annoying. We're just going to wrap it around our can, and a can is ever so slightly smaller than half an A4 bit of paper. So just cut slightly to one side of the halfway line and keep the shortest bit. Lara, this is an awful lot of effort for an activity that you discovered on Facebook yesterday. Doesn't work. Yeah, I know, but it's about understanding and remembering. And we're definitely doing those things. So you should have a slightly less than half a piece of paper with these weird little rectangular creases in it, which we need. Okay, let's mark the homework and then do something else with this. I say mark the homework. Don't worry, don't get that dreadful feeling that you used to get like in school, if you've ever been to school. This, you know, I can't see you and it doesn't matter. Energy is transferred from this hot mug of tea to the surroundings, the air. Complete the sentences below using the words conduction or convection. Energy is transferred through the sides of the mug by... That should be fairly easy for you, I hope, at this level. The mug is a solid, right? So the hot particles of tea are knocking against the inside of the mug, and that is passing heat energy through the ceramic mug. So that is convection. Conduction. Conduction. There's a lot of con words. That's conduction, because it's a solid. In the air around the mug, energy is transferred by convection, right? The air here heats up, so it rises, so then cold air takes its place, but then that gets hot, so that rises. A tiny little convection current next to your mug of tea. This picture shows ice being used to cool some hot coffee. It's quite a tricksy question, this. How is the coffee at the bottom of the glass being cooled? So the ice is at the top. How is it that the coffee at the bottom is getting colder? Well, the cold coffee is slightly denser, right, than the coffee down here, which is warmer. So it sinks. And because it's sunk, this warmer coffee's got to go somewhere, and it's less dense, so it rises up. And that's a convection current. So that was B. And finally, the gap between these hot and cold objects can be filled with air, iron, a vacuum, where there are no particles, or water, which will allow thermal energy to pass between the surfaces the fastest. Well, it's obviously not air, right? And it's not a vacuum, because those are both good insulators. They hardly let heat pass through them at all, we learned last week. Water's a liquid. It's not a terribly good conductor. It's going to be iron, which allows energy to pass quickly between them. Okay, let's do it. I'll just set you off on a bit of a colouring mission, and then I'll start to tell you about radiation. Right. So, two of these rectangles, you need to colour them in black. Don't do the rectangles at the end. Do the two have half a rectangle gap, and then colour in those two rectangles black. All right. I've got 3 black pens here. I'm on my 3rd black pen. But yeah, just colour it all in black. If you're super good at colouring and you manage to get it done while I'm telling you about radiation, you could colour in the other side as well, so that both sides are black. That would be even more effective. I don't know what I'm trying to do. I'm not going to colour it in front of you. That would be a terrible lesson. I will tell you a bit about radiation. You don't need to know this for this bit of learning about radiation. Like when they ask you about conduction, convection and radiation, they're not going to ask you about this. But I just thought it's just interesting. It's really interesting. And like I say, there's no bell going off. There's no pressure here. So I'm just going to tell you it while you're colouring in, all right? History. In 1819, Danish scientist Hans Christian, I'm going to say Ørsted, was giving a lecture involving magnets and electricity. In the middle of the lecture, he just happened to put a compass down next to an electric wire. If you're looking at the screen, this is exactly what happened. Pupe. And what he saw surprised him. This is what he saw. You ready? This took me ages. Yeah, the compass started moving. What is that about? Well, inside an electric wire, charged particles are moving, right? If you've done my electricity model, you know this, probably electrons are moving around inside a wire. Charged particles, like electrons, are surrounded by electric fields, just like magnets are surrounded by magnetic fields. You don't need to remember this yet. So it turns out moving electric fields, like what you've got generated by a wire, create magnetic fields. And obviously that's a compass, so it was detecting the magnetic fields, and that's what was messing with the compass. This is, like, as far as I know, the biggest, or if the only, scientific discovery to be made in front of a huge audience of people. So well done you. Along comes Scottish scientist, an absolute legend, James Clerk Maxwell, who says, oh, well, there are charged particles everywhere. Maybe space is full of these electric and magnetic fields, like, interacting with each other. And maybe those fields vibrate as waves. And they travel at, maths, 300 million metres per second. And he was right. We are, right now, wherever you are on the planet, you are surrounded by electric and magnetic fields. And when they vibrate, just like when you wiggle a slinky, you get these waves. So we give these waves different names depending on how long they are, right? We did this. You recognise this from the waves module if you've watched that one. So this is what happens. Like, if you imagine you can make a slinky do very short waves or very long waves, this is just what electric and magnetic fields are doing all around you. You've got long waves, which the longest ones we call radio waves, slightly shorter ones we call microwaves, and the ones that are kind of in the middle, yeah, we just call them light. And your eyes just happen to be able to detect electromagnetic waves that we call light of that wavelength. All these waves are essentially the same, though. That's the important thing to remember. Like, they all travel at the same speed, the speed of light, because one of them is light, right? And none of them need any particles to travel. So it's not like conduction and convection. If there's no particles, like space is a vacuum, it doesn't matter. These waves can pass through it. The hotter an object is, the shorter the average wavelength of the wave that it gives off, all right? So the gamma is incredibly short wavelength, very dangerous. Radio waves have the longest wavelength. The very hot stars give off waves that have a length that we call them ultraviolet waves. Our sun gives off, I mean, everything gives off really all electromagnetic waves, but our sun gives off mainly light. And it just so happens that objects on Earth, including humans, like all objects on Earth, I can't emphasise this enough, literally every single object on Earth, everything, gives off these length waves that we call infrared radiation, infrared waves. So obviously not everything on Earth is hot enough to give off light, but everything is hot enough to give off this kind of wave. You're with me? So the hotter something is, basically the shorter the wavelengths it can give off, and everything on Earth is the right temperature to give off infrared waves. So we think of it as being thermal radiation. It's a bit of a sort of mistake people make, thinking that there's something special about infrared radiation, which means that it's hot. That is not true. Like, all waves have a warming effect. It's just that infrared is particularly special because everything gives it off. Like, our eyes can only detect light. But if you could build something that could detect infrared waves, and humans have, then you can just see everything. It's brilliant. If you've done my waves module, you've seen this before. So this is a picture of a car going down the street, but with a sensor that can see infrared instead of light, right? So the cooler bits are in purple. So, like, the road is quite cold, so it's not giving as much infrared radiation off. And the wheels that are whizzing along the road, they're very hot. So they're showing as white because they are hot. They're giving off more infrared radiation. Yeah? It's good, isn't it? So all you actually need to know for your exam for this bit is that thermal radiation is infrared radiation, and all objects emit this radiation, right? That's just what I said. All objects give off infrared. And if you see the words thermal radiation written down, they mean infrared. And you also have to know that thermal radiation, infrared, thermal energy transfer by thermal radiation. That just means heat being transferred by thermal radiation. Does not require a medium. A medium is like a thing, particles. So basically that second sentence is just saying thermal radiation doesn't need particles to travel. Whew. Okay. Hi. Right. We better start learning about radiation. So maybe you'd better do a little bit more on your Leslie cube. Yeah. If you've got your piece of paper and you've coloured in 2 of the rectangles black, the next thing you need to do is to stick some foil to the other two rectangles on the far side. I think the easiest way to do this is to get some foil and put the end of your paper over it, like the last 2 rectangles over it, and then just cut out the foil. Yeah, so you've got a piece of foil the same size as 2 rectangles, and then just sellotape it on. If you can, sellotape it at the bottom and the top. Don't put a big slap of sellotape along the middle, but it's hardly going to matter. Yeah, different materials behave differently when infrared radiation shines on them. This bit is hopefully fairly easy to get, right? Because obviously light is very similar to infrared radiation. So if I said to you, I've got this black sort of slightly furry jumper on and I've got some tin foil here, which one, the tin foil or the jumper, do you think is reflecting light more? Which one of these is reflecting more light? Yeah, it's definitely the tin foil, isn't it? And infrared radiation behaves in exactly the same way. So shiny things reflect infrared. Obviously, we can't see it, but it is happening right now. Whereas black things absorb infrared and then emit it. This is quite weird. Maybe I should draw a thing, because some people on Facebook were getting a bit confused about this. So here's a square and it's shiny. Infrared radiation shines onto it and then it just bounces off again. It is reflected. And the same thing happens with white. Let's just draw it. The same thing happens with white things. Radiation is more like it's just bounce off something that is white. Something that is black, it absorbs it and then it emits it again. So when radiation shines on something that's black, it goes in, it absorbs it, and then I'll draw wavy lines to show that it's emitting it again. So it kind of does take it in, if you see what I mean. Yesterday on Facebook, people were saying things like, oh, does it reflect it and then emit it? I was like, no, that's not, that you can't do that, because if you're emitting something, it means you're sort of giving it off. And if something's reflected, it means you haven't got it in the first place. Does that make sense? Anyway, the only other word you need, you might know this if you've done any like posh painting. Matte with a double T is like the opposite of shiny, all right? So my jumper is matte, it's not shiny. So shiny and white things, radiation just bounces off them, reflects off them, whereas black and matte things, I don't want to say soak it up, but you know what I mean, they absorb it and then they emit it again. In your homework PDF this week, which is already up in my Facebook group, I've linked to a couple of websites that talk about black bodies, which you do need to know about, but I won't talk about them here. Right, I'm just going to be really mean, because I couldn't even do this. Kind of had to Google it. But I want you to come up with some examples, please. So white and shiny materials are good at reflecting infrared radiation. Black and matte materials are good at absorbing and then emitting radiation. Can you give me some examples? I think the examples of how we use white and shiny things to reflect infrared is much, much easier than an example of something that humans have made it black or matte so that it's good at absorbing and emitting radiation. The example that I will give you to kickstart you is astronauts wear white, don't they, or shiny outfits when they're moonwalking to reflect the radiation given off by the sun, okay? And if you're like, oh, this is so easy, I've done it already. All right, then why are radiators white? Why are radiators white? Should they not be emitting radiation? Surely the whole point of a radiator is to emit radiation, to put heat into the room. So why are they shiny? So hopefully you've come up with a couple of ways in which, a couple of examples of how humans use white or shiny materials to reflect infrared and why that's a good thing. The black one you might be struggling with. I'm going to go and get something from my kitchen that I think is a good example of the black and matte one. So the sounds might give you a clue. I'm still struggling to think of anything. was getting some excellent answers to the radiator question yesterday on Facebook. I think only one person got it right though. Okay, I'll give you 10 more seconds. Teacher seconds, it just means as long as I want. Okay, so I'll give you some examples. White houses in hot countries, they are painted white so that they reflect the heat from the sun. If you've ever wrapped some food in tin foil, well, aluminium foil I should be saying, shouldn't I? That was because the food is giving off a lot of infrared radiation because it's very hot. So if you wrap it in silver foil, the radiation reflects off the silver foil and sort of goes back into the food, so it doesn't escape, so the food stays hotter for longer, right? And if you've ever seen anyone who's run a marathon being wrapped in a foil blanket, that's why. They're basically being treated like a human baked potato, yes. The silver foil traps their body heat, reflects heat that is being emitted from them as radiation back towards their body, so keeps them warm, yeah? The black one of these is just like the classic physics teacher answer. So stoves are black, so they emit heat into the room. Obviously, if this stove was shiny, I can't not say shiny. No, that's my favourite film. If this was shiny, obviously the heat from the fire would just reflect back into the stove, which is no good at all. You want the stove to heat the room. And the back of your fridge. If you want to go on a little exploration to the back of your fridge right now and check it out, it's probably quite dark because obviously a fridge's job is to get heat away from the inside of the fridge so the fridge stays cold. So the cooling fins on the back of your fridge are quite possibly black so that they radiate that heat away as quickly as possible. I suddenly thought, I've got this pan, this cast iron pan, which is black. And quite matte, you see that? It's not very shiny, it's kind of rough. So I guess, the bottom of this frying pan, it's just fascinating, isn't it? It's just, this IGCSE physics just gets more and more interesting. The bottom of this pan is very shiny, but I reckon that's because it's probably because if you put it straight down on a hob, heat will pass through the pan because of conduction, right? So the particles in the metal are very close together, so they're touching the electric hob or the hob, and that heat would pass through that way. Whereas this one, this might be better if it was a gas hob because there'd be a flame here. So mostly heat would be travelling to the pan via radiation, right? So it would just be like air in the middle. So that way the whole pan would get hot and then emit the heat out again. Okay, right. How are you getting on with your Leslie cube? If you've got it to the stage where you've got 2 rectangles that are silver and 2 rectangles that are black, you just need to wrap it around your can and fasten it with sellotape, and then you'll have something like this. Yeah, it's nice, isn't it? I mean, it looks nice. It looks proper physicsy, even if it's not going to end up working. Radiators. What is with radiators? Well, it's sort of a trick question, I suppose. Most walls are white, and radiators, they're really just white because they're designed to blend in. It would be better if radiators were black. You've got hot water inside the radiator, so it would be better if that hot water gave off radiation that was absorbed by the radiator and then emitted into the room. But it doesn't really matter because we learned last week that radiators really, confusingly, work mainly via convection. So they heat up the air above them, that air gets less dense and therefore rises, and cold air comes in to take its place, and so on and so on. So yeah, radiators. Working because of convection. I don't know. I didn't make these rules up. Okay, right. While you're finishing off your Leslie cube, I've got a little challenge for you. I'm going out for an hour. You are in charge of keeping my coffee hot. You look around the room for equipment to help you complete this vitally important task. And this is what you find. You do not need to use all of this stuff. I cannot emphasize that enough. You definitely don't need all of this. But imagine that you've got some newspaper in front of you, some shiny black fabric, some thick wool, I don't know, some loft insulation that you've found, some bubble wrap, some aluminium foil, some scissors, some tape, and some string. Try out a few designs. What can you do with all this stuff? How are you going to wrap my mug up to keep the coffee hot for an hour, to have it be as hot as possible when I get back? If you've got the printout for my Facebook group, I drew you 3 mugs. I didn't draw them. I put you 3 mugs on the sheet so that you can have a little experiment and cross stuff out. How long shall I give you for that? I reckon a minute? I'm going to do one too. You can layer up. That's important. You're really going to have to think about this. You can wrap it up as much as you like, but I don't think you'll get anywhere if you just throw everything at it. That you're going to have to decide which ones of these you want to miss out. Oh yeah, I've even improved on my design from yesterday's lesson, I reckon. Okay, right, I've done mine. How have you got on? Come up with something? When I used to teach in a classroom, I used to just dump a load of stuff on the table and put them in groups and say, you've got to wrap your... I just gave them all a hot cup of water and said by the end of the lesson, whoever's was still the hottest, like, won a prize or something. So I'm taking this very seriously. Right, here's what I've done. So you had to think about what materials you would use, okay? Paper, like if you've got some paper in front of you, it's white, isn't it? So you might have been thinking, oh, the newspaper's quite white, so that would reflect the heat that the coffee was giving off. But it's also matte, isn't it? If you feel it, it's not very shiny. So I think you're better off using foil. I wouldn't have used the paper at all because foil's better at reflecting than white matte paper is. So I've put some foil on the top. Well done if you did that, if you were thinking that the hot coffee, it's very hot, so it's giving off a lot of infrared radiation, and foil will reflect that back into the cup. But did you think about that foil is also a metal, okay? So metal is actually very good at conducting heat, isn't it? So I've put some wool on top as an insulator so that any heat that does conduct through the foil is going to get stopped by my wool. But just in case there is any heat getting through my wool, I've put another piece of foil on top to reflect that back in, okay? On the sides, I didn't put any foil right touching the sides of the ceramic cup. Hopefully you didn't do that either. If you did, scribble that out because the sides of the cup are solid, aren't they? So heat is going to be travelling because of conduction all the way through the solid walls of the mug. And if it just meets a solid wall of metal, it's going to travel very easily through that mug via conduction. So I've put some wool there because that's an insulator to stop heat getting out because of conduction. And then I've put some foil on top of that so that anything radiated through the wool gets reflected back in. And I didn't do this yesterday, but I suddenly thought, if it's sitting on a table and the table is a solid, I mean, wood has got quite a lot of air trapped in it, so it's not a great conductor. But just to be on the safe side, I mean, it's not terrible. Don't do this in real life, it's not very safe, is it? But I've put some very robust bubble wrap on the bottom because that's got air bubbles in it, and air is not a very good conductor at all. It's an insulator. I thought about putting wool there, but I think bubble wrap, it's got more air in it, right? So I think, and also it's wrapped in plastic, isn't it, the air? And plastic is a good insulator as well. So I think bubble wrap is going to keep it hotter than if I put wool there. But I don't know. I'm never going to try it. I love coffee too much to mess around with it. Right, very quickly then. Oh, I just rubbed all that off. Never mind. It's on YouTube. Have you got some sort of just boiled water so that we can fail to make a Leslie cube? What you do is, and again, this is like really quite silly and dangerous. Like obviously metal, the can, is a very good conductor. So if you pour very, very, very hot water into a can and then you touch it, you are going to burn yourself. So wait for a little bit, please. We'll do this right at the end. But what I want you to do now is to just pour very hot water into your can. And put the whole thing on a bowl, right? Just or on a plate or in a bowl, just in case it leaks. There we go. So I've just put some very hot water into my Leslie. I'm going to keep calling it a Leslie cube because if you call it a Leslie cylinder at IGCSE, you won't get any marks. It's a Leslie cube, okay? I'm just going to leave that there for a bit. How does snow behave when radiation shines on it? It's a good question, isn't it? How does snow behave? Lesser mortals might just say it melts. Well, yeah, it does a bit. But also we know that snow is white and ice is shiny. So it actually bounces off. This is why you can easily get sunburnt when you're skiing because the infrared radiation is shining off the snow and hitting your face, right? That's why you've got to put a lot of sunblock on if you ever go skiing. Why is this related to what we're talking about next? Well, very quickly, you need to know about kind of the balance of radiation on Earth. So obviously radiation, infrared radiation, thermal radiation is coming to Earth from the sun, and there's some of it is being absorbed by Earth and some of it is being reflected. And this balance of how much radiation gets absorbed and reflected and emitted is incredibly important for keeping Earth's temperature more or less constant. I've put in my printout, and I've got it here for you, a diagram which is ludicrously more complicated than you would ever need, but I could show you it for free. So here we go. Here's the incoming solar energy, so that's just 100% of the infrared radiation that comes to Earth. And you can see some, you don't need to know as much as this at all, but some of it is just reflected off the atmosphere, just like bounces off. Some of it's reflected by the clouds. Some of it is reflected from Earth's surface, so the snow and ice is particularly good at doing that. But some of it is absorbed by the clouds, absorbed by the oceans, absorbed by the land, absorbed by the clouds, and then the clouds radiate it out again. So this is how Earth remains a pretty much constant temperature. We've done a global warming lesson, haven't we, at the end of our weather lesson? But yeah, it's obviously closely related to global warming because Earth is getting hotter. And one of the things we looked at in that lesson for all ages was how, because the snow and ice are melting, because Earth is heating up, not as much radiation is getting reflected, and therefore Earth is heating up. So it's kind of this vicious circle, yeah? More heat absorbed. Yeah, you get it. Right, let's... I tell you what, I was going to talk about the Leslie cube, but I think we'll talk about the Leslie cube just at the very end. I want to give you, to finish off, one of the tricksy best exam questions I have ever seen. This is one of my all-time favourites. As a teacher, like marking people's answers, I was not a fan of it, but it is brilliant. It's one of the hardest, trickiest questions I've ever seen at GCSE, and it has to do with radiation. What do you make of this? They showed a picture of a patio heater, yeah, like you get sort of in beer gardens and stuff, where people can sit out if it's cold, but still enjoy the outside. And they said the very top of the patio heater is shiny. And they said, why? They just asked why. Why would the very top of a patio heater be shiny? it was a brilliant question because everyone knew loads of stuff about, everyone gave really good answers, and I'm sure most people writing the answers sort of knew that they were wrong, but they couldn't work out why they were wrong. So a lot of people said to reflect heat back to the people below. That's quite possibly what I would have written. But you know that's not right, don't you? Because it's on the top. So even as you were writing that, thinking, oh, maybe I'll get a mark, you knew that it wasn't, because that would be why the bottom of the patio heater was shiny underneath. It doesn't explain why the top is shiny. Some people thought, no, that's definitely not right. So they wrote things like to reflect heat away from the heater. Maybe like so that the sun bounces off it. But obviously that's not right either. And have you got it? Because teachers like me, they were constantly teaching people, shiny things are very good reflectors of infrared. And what a lot of us forgot to say is that if something is a very, very good reflector, it's a bad emitter and absorber. And the answer was, it's got a shiny top to stop radiation being emitted from the top of the heater. Isn't that brilliant? So if the top of the heater had been black, obviously it would have absorbed infrared radiation from below, and then it would have emitted it, so that heat would have got lost. But shiny materials are very bad at absorbing and emitting radiation. So good and so annoying. But honestly, round of applause for whoever wrote that. Anyway, moving on. So just be aware, black matte objects are bad reflectors, as well as being good absorbers and emitters. This is a Leslie cube. It's a lovely little thing. It's just you will see in your exam specification, just quickly before I go, it says you need to know about like experiments that can be done to work out what kind of materials are good emitters and absorbers and which are good reflectors. And a Leslie cube is a nice way of doing that. It's just a cube, and it's got like one matte black surface and one shiny black surface and one matte white surface and one very shiny kind of silvery surface. And you just fill it with boiling water through the little hole in the top. And you leave it until the whole thing becomes the same temperature, which is really weird. We are going to do more about temperature in a few weeks' time. But yeah, the hot water inside is obviously just one temperature, so the walls of the container become all one temperature. But if you look at it with an infrared detector, you see weird and beautiful things like this. So here's the photo. Obviously, this is the black side, this is the shiny side. And you can see there's absolutely loads of infrared radiation being given off from the black side. And the shiny side, there's hardly any. There's so little that you can actually see the infrared radiation of that person's hand reflecting in the shiny side. Isn't that great? So that's what I was thinking that we would make. But it hasn't worked. But I wonder if you can tell me why it hasn't worked. Obviously, do not do this. Get an adult to check if you're not sure. If the sides of the can are very hot, don't touch it. But once it's got to a safe temperature, I was thinking, I'm doing it right now, we could not look at the can, spin it around a bit, and then just get like the tips of your fingers on either side of the can and touch it and see if you can tell which side feels warmer and which side feels cooler, and see if it's right. So you would expect, wouldn't you, that the side that you'd coloured in with a black pen to be slightly hotter? And we are just not finding that. I'm sure when I practiced this, I would never do anything without practicing it first. I'm sure I really was totally convinced that the black side was hotter. Well, maybe. It's just not a very good test, is it? Because obviously, like pen is kind of a liquid, isn't it? So if you've coloured something in with a liquid, you could say, well, you've made the paper wetter, and therefore that might affect the results. The other reason why, a lot of people were saying that the side where you've put the foil feels hottest, and it definitely does actually. Like I say, please be careful. I'll get so told off if you burn yourself. But if you feel that the foil side and the paper side, the foil does feel hotter, which is not what you'd expect. But why is that? What have we done wrong, basically? Why was this never really going to work if I'd thought it through? Why was our metal side always going to feel hotter? But in an actual Leslie cube, you can see that the metal side is giving off the least radiation. This is such a good question. So it's making us think more than if this had worked. Why on our Leslie cube are we detecting a hotter temperature on the metal side, but on a proper Leslie cube, you detect more heat on the black matte side? Have you got it? It's because when you were detecting the radiation here, you would have used, if you got those thermometers that someone just puts in your ear and presses a button and it goes beep and it gets your temperature. You would have used something like that. You wouldn't have used a detector that actually was pushed up against the side of the Leslie cube. So you're definitely just detecting whatever radiation is getting to that detector, right, through the air. Whereas what we're doing is, our method of detecting the heat is by touching it with our hands, isn't it? And obviously if you're pressing something metal against something hot, then the heat is conducting through the metal. Did you get that? I think that's what it is. We're touching it, so we're feeling that heat because of conduction. We're not actually detecting radiation. If you've got one of those cool beepy thermometers, put it on all the different sides if you can, please, because mine's run out of battery. Or you could, I suppose, hover your hands really near it until you feel a difference. Anyway, I feel like we've done enough on our terrible Leslie cube. If you go to the homework PDF, which is currently waiting for you in my Facebook group, there's quite a lot of write-up, like from BBC Bite Size, about Leslie cubes, which will give you some more information on that. Right, that is the end of the lesson, and therefore that is the end of the energy module. Thank you so much for joining me. I think most of you are, anyway, and I feel bad about banging on about it, but oh my goodness, these lessons are so much work. Like, I can't tell the others because actually not that many people come to these lessons, and I put far more time and effort into them than I do into the other lessons because I just love it, and I am a physics teacher. But yes, I am extremely grateful for people who are choosing to pay me for the vast amount of work that I'm doing. It's just lovely, and like all the comments as well and the feedback have just been really nice. So I can't stop doing it, but I do really appreciate the fact that people are sponsoring me. So if you want to go to my About section and click the website that says coffee, is it Ko-Fi? Loads of people have started using it recently and everyone keeps saying Ko-Fi, but I've been saying coffee for 3 years, so I'm not going to change it. Go to the website called Coffee, search Theatre Science, send me £5 a month and I'll send you nice things. I'll send you magazines. I am going to my Facebook page if you're watching live. I am getting there. So I'm going to say hello to you if you've commented. If you support me with £5 a month, I'll send you some diffraction glasses, which make you see rainbows. Oh, they're amazing. I'll send you some stickers, and I'll send you Theatre Science magazine. Support me with £5 a month. I'll send you my favourite past magazine. It's got a biodegradable, home compostable plastic bag. They cost quite a lot more, but I got them so that you can make this little tray, put different bits of food in it, grow mould, and then compost the whole thing. It's got a choose your own adventure story. You're a mould expert in a museum. Will you be fired or promoted? It's got a beautiful comic with a very in-depth version of how penicillin was discovered, because a lot of people don't know the true story. And if you support me with £6 a month, you get that magazine, but you also get the latest magazine, which is on weeds. Because I just love, it turns out I love weeds, like the little boring plants that just people try and kill with weed killer. I just love them, they're amazing. A lot of them are genuinely extremely good for you. Oh, people have commented. Oh, Aaron and Hope, hello. Oh, that's nice. Yeah, some of them are good for you, not if they've got weed killer on, but I have talked about weed killer as well. There's a little card game so you can learn the names of the different weeds. There's quizzes, there's activities. I'm very proud of Theatre Science magazine. Thank you very much to everyone who's receiving it. It's like, honestly, it's like writing you all a letter. Hello, Samuel. Patiently waiting through all that chat that you've heard before. Who do you see ultraviolet of your eye? Wait. Aaron says, who do you see ultraviolet of your eyes see up to light? Aaron, I'll come back to that. Henry, who was getting very stressed about these questions. Henry, did you sort yourself out? They were all right, you know. The radiator thing is what, hang on, what? I don't know what I'd do without your feedback, honestly, guys, I don't. Henry, name of the coffee device. I heart coffee minus the R. Oh yeah, that's good. I heart coffee minus, so I heat coffee. That is genius. Very good. Right. Henry, Henry's full of the lols today. I've put say hi here if you watch live, and Henry's written hi here if you watch live. Right. Aaron and Hope are here. Hello, Samuel's here. Aaron, who do you see ultraviolet of your eyes see up to light? Aaron, you need to sort out your people, mate. Who typed that? Come on, type it again. How do you see? How do you see ultraviolet? Is that what you're saying? How do you see ultraviolet? With your eyes. What? Are you asking about like ultraviolet He's saying, how do you see ultraviolet with your eyes? This is an excellent question. Okay, we've finished the lesson, so I'm just going to go back and pull up this little picture of the waves then. If you're asking how you see ultraviolet, because you do sometimes get told that you're seeing UV waves, don't you? Like, I've got a pen with a cool light on the top. Like you can write in secret writing and then shine the pen on, and it says it's a UV pen, but you're quite right, you can see it. So what is that about? Right, I'll just pull this up again. What it is obviously the electromagnetic spectrum is a spectrum, so it's not like nature hasn't decided that these waves are radio waves and these waves are microwaves. It's just that once a wave gets to a certain length, humans change the name of it. So where's the thingy thing? Here we go. So here, there's no like definite line between light that we can see and ultraviolet light. It's just gets longer and longer and longer. So I guess what those pens are doing is they are giving off ultraviolet light and also light. And the light that you see will be purple, okay? We did this in waves, we haven't done this here, but red is over here. Red light has got the longest wavelength, and that goes through the colours of the rainbow, and they get shorter and shorter. So red, orange, yellow, green, blue, indigo, and violet light has got the shortest wavelength. And obviously then it becomes ultraviolet. So, so yeah, the answer is we cannot see ultraviolet light, but if you're looking at a very, very violet light, it's probably giving off quite a lot of ultraviolet waves as well that you can't see, but you can see the violet light. This is what those pens. Does that make sense? I can go back to my Facebook page and have a look. Can't I? Oh, are solar panel, hello, Samuel, are solar panels an example of black things that are made to absorb heat? Yeah, that's a really good one, isn't it? Oh my goodness, we just did solar panels and solar cells. Yeah, exactly. Wow, nice one. In fact, we've probably got a picture of that, haven't we? Right, I'll refresh that to see if anyone's written anything else. Yeah, of course. Was that literally just a couple of lessons ago we looked at solar panels, didn't we? I'm going to pull up the picture, which is brave, because if they're not black, I'll be very upset. Ooh, yeah, kinda. I mean, just looking at this diagram that I showed you in another lesson. So actually, yeah, it's the opposite. Well, yeah, solar panels are dark, aren't they? I must admit, I don't know if that's to absorb infrared radiation or not, because solar cells generate electricity by, like, yeah, ultraviolet light and waves shining off them like lights. But I don't actually know if the temperature makes any difference to how much electricity flows, or if it's the brightness. Sorry, I think it's the brightness. So like a solar cell, you remember this? Solar cells have got semiconducting material in, right? And when light shines on them, we've said that electrons kind of pop off that material and start moving, and that's what electricity is. I'm pretty sure, you're making me doubt myself, and if I was planning the lesson, I would Google it just to be doubly sure. But it's the light that is popping off those electrons and making the electricity flow. It's not the heat, is it? Because if it's a really hot day, but your solar panels are in the shade, they don't generate as much electricity as if they were in the sun. So it's not about temperature, it's about light, I think. Can't believe this is recorded forever, but or maybe it doesn't matter. I don't know. I need to go away and Google it. If you're watching this and you're like a physics teacher and you're tutting at me, I'm gonna go away and Google it, okay? It's not all in my head yet. But yeah, the other kind of solar panel where like a solar heating device where it's just water in the pipes. Yeah, you would definitely think that those pipes would be black because that would help to absorb and therefore heat the water inside. Yes. So the kind of solar panel where it's heating water, absolutely. The solar cell where it's generating electricity, not sure. Is the short answer. Oh, more comments. Yeah, I love this. Let's see. Newest comments. That's what I meant. Oh, good. That is what you meant. Brilliant. Ah, what a nice way to end the lesson. Excellent. All right, you lot. Thank you. That was nice. Get some proper conversation going, even though we're on YouTube. Okay. Yeah, as you probably know, no Lego Story Show this week because I'm at this Institute of Physics Science Communication conference, like a grown-up going to a conference tomorrow in London. But everything will be back to normal next week. So I will see you then. Thank you for coming. Bye.